no offense. But the geology professor gave the same exam every semester. It was in a blue book, but he'd scramble the questions. So if you knew you were taking geology the next semester, you would go and take photos of the exams and the answers the semester before. And so there's no challenge to that, really. Everyone was getting an A, pretty much. So I said, you know what, I want to challenge myself. So I took classes in chemistry and polymers, actually. So most of you probably don't know that. So instead of taking geology, I chose polymers and chemistry. And I love doing that because you could blow stuff up in chemistry. And I was a civil engineer. It was kind of expected, right? And so I enjoyed that very much, doing that. So what I was going to talk to you today about is different polymers we're developing from, we call it soybean oil, but it's various vegetable oils. Now, most of us think of soybean oil going into food, right? How many people think that the majority of soybean oil actually goes into food? And most of it doesn't go into food, and most of it you wouldn't want it to go into your food, okay? So we get into this kind of Washington, D.C. centric aspect of food versus fuel debate, right? And the fact is these are not things that are going to be competing with food, okay? I do want to recognize my colleagues, Eric Cochran, bright guy. He's a National Science Foundation Career Award winner. He won it in his 3rd year as an assistant professor. So that basically means he's the top polymer guy in the United States as an assistant professor in his generation. And he's now associate professor and on his way to being a full professor. Naku Hernandez, he works with us, one of Eric's former students. He's a professional scientific staff person. Andy Cashone, he did this work as part of his doctoral thesis. He now works at Flint Hills, previous AMAP scholarship recipient. Savannah Chen, who's worked on this for her master's and PhD degrees. She's continuing on her PhD right now. Austin Homan, he's another professional scientific person. As we're gearing up our pilot plant, he's actually going to be one of the pilot plant operators. All right, so I quickly recognized that I was going to be last on the docket before the bar opens. So I have to integrate some of these different concepts and philosophies here. So back when we started getting into this work on the polymers, we found that we had some good results, but getting consistently good results was a challenge. There's a lot of different factors that go into making any polymer, let alone something with vegetables vegetable oils that people haven't done before, right? So we followed, get a good idea and stay with it, dog it, and work at it until it's done right. The guy who said that was actually Walt Disney, okay? So we have over 110,000 hours, maybe 120,000 now, of research and counting into this work. So I've been asked to summarize our work in 30 minutes or so, 110,000 hours. So there's a lot left out that if you have questions, you're welcome to ask me. We all know butadiene. It's a byproduct of cracking ethylenes from crude. But you can get ethylenes from natural gas, right? Natural gas prices are fairly low too. But we don't get butadiene as a co-product from cracking natural gas. It's a gas phase explosion hazard. We have polymerization of styrene, butadiene, styrene. Look at the anionic polymerization process. It can be expensive, oxygen sensitive. Looking at organometallic initiators. Okay. So when we look at soybean oil, we're really looking at triglycerides, and we're looking at generally 4.6 double bonds per molecule. And then when we're looking at that, the modification, we can use different polymerization techniques. Okay? So we had a colleague of ours that would make epoxy-like materials. And, you know, epoxies represent a certain space in the polymer market, but they're a fairly small percentage, right? And so we took Rich LaRocque's approach, and we said, you know, is there some way we can arrest that process before it gets to that epoxy state, and we still have thermoelastic properties? And so that was the working idea. And we got into doing this because of the lack of polymers in Iowa in 2007, 2008. And the Iowa DOT said, Chris, what are we going to do if we can't use polymers anymore in our pavements? I said, well, can we develop polymers from different sources? And so we began from that basis. Okay, well, you know, people had prices up here in polymers and stuff, but you can see the effect of the Beijing Olympics, and we can bring that timeline out to today and see those price fluctuations in butadiene. But we can also see the spot price of soybean oil. Okay, so when you look at balancing risk and reward, volatility is part of that function, right? So you can see that if I'm producing polymers, do I want high level of variability in pricing and what that means to my customers? No, I don't. I want a little bit more stable pricing, and that provides me with lower risk. We can also get the triglyceride molecules out of dry distiller's grain corn oil. So after they can squeeze more oil out of the dry distiller's grain, and then they can still feed the dry distiller grains to animals for feed and stuff. So those prices generally follow soybean oil prices. Okay. Well, butadiene, it's not safe. In Louisiana, there's a plant problem, 73 injured, 1 dead, June 2013. It's expensive to transport butadiene, $300 a ton. Okay. We had a derailment south of Louisville in November. All right. So see, they're trying to keep the tanks cool, so we don't blow them up, basically. All right. So the question becomes, how are we going to use these vegetable oils in producing polymers? We use a radical polymerization process. Okay, and there's two different types. We won't go into a lot of detail on the two different methods, but one is the atom transfer radical polymerization, which we refer to as ATRP. And then there's reversible addition fragmentation chain transfer, or RAFT. Now, in RAFT, we have an option of building our polymer chain on the end, but we've also developed a system where it's like a gearbox. And so as these gears are spinning in the middle, we can actually grow the chains from the middle with a gearbox kind of system. Gears turning out, the polymers in the middle. And we can control the molecular weight and the chain of these polymers very, very well. So our preferred process right now is the RAFT, actually. Okay. Well, you know, what's exciting about this is that these polymers came from the asphalt industry, right? Asphalt folks coming up with new polymers that can go across the entire spectrum of the polymer industry, okay? And we're only one small component off the total polymer industry. So I think that speaks to the level of innovation that we have in our industry. So we're just the one little leaf there on the bigger polymer tree here. Okay. So one of the things that you want to look at is the functionality of these polymers. And so when you look at the degree of acylation, if you will, okay? And this is just a DSC looking at the glass transition temperature, okay? And so we're seeing is glass transition around minus 26 centigrade off of this particular monomer that we put into then our polystyrene polymer. Polystyrene, we call it PESO, polyacrylated epoxidized soybean oil. And then we can change that functionality down lower to 1.1. And we can drop the glass transition temperature down lower. Okay, so we can tune these polymers based on end market opportunities and things, right? And so we actually can look at our glass transition as a function of the acrylation, degree of acrylation and their functionality, okay? So this took a fair amount of time to develop this, but this helps us understand how to produce these polymers. So if we're at a higher level of functionality, we're going to need to use different solvents than we're used to using in producing polymers. So the one that we've selected when we're up at the 2.5 range, we need methyl THF. Okay? Well, that's a little bit more expensive. All right, and then we can do those polymers, and then we can look at the effects and modifying asphalt, and we can take a PG 51 grade and make it a 64, or we can even push it up towards a 76 with 3% modification. But if we drop down in this acrylated group functionality, we actually can now move towards using a cyclohexane, which is more off-the-shelf solvent producing polymers, and then the solvent removal process is easier. But we also find that we get better conversion quicker in producing our polymers. So we can move from 10 or 12 hours in producing the polymer now down to the 6-hour range. Okay? And then on top of that, we also able to reduce our styrene content down to around 10 or 15%. We typically are using what, 30, 35% styrene in our polymers. Styrene's the more expensive component today in the polymer. This just shows you doing some DMA work where we get our glass transition temperature. This is again a 2.5 functionality. And it just highlights that we're about minus 12 centigrade. Okay? We go to the 1.5 functionality, we drop it down to minus 25. We can drop it down to, like I mentioned before, to 1.1, and we're about minus 32. Okay? So that's pretty impressive. So most of the people in the asphalt business that use polymers don't know what goes into making that a friendly material to use, right? We need to have storage stability, and we need to have what? Inhibitors, right? Polymers are always reacting and chaining out, okay? And so what are we doing to inhibit that process? So we have to look at kind of the standards that we have. Often people are using an Ethanox 310, and then we're trying to find out where we can get our blend temperatures up with the polymers in the asphalt, okay? And so we can use a methyl hydroquinone to help as our inhibitor, okay, and stretch that out. And so we've gotten out that way with a methyl hydroquinone. We actually use some other ones we can't really get into a lot of conversation about right now. It stretches that even a little bit further out there. This is a busy graph, but again, this is just highlighting that we can see the cross-linking temperature, again, out towards that 220 mark, and we call the order-disorder transition and stuff. And then this highlights the 30 versus 35% polystyrene content, and we're inhibiting at 1.5%. All right, so if we drive that polystyrene content down, lower, and then we look at things, we can drive these inhibitors to these temperatures being quite a bit higher. All right, so let's go into asphalt modification. This is just shows the hard block and the soft block components of a typical SBS polymer and asphalt. Okay, and Shell/Kraton is really the market leader developing this technology and implementing it. We can go in and take an asphalt from Flint Hills. We refer to it in the Midwest as an XX-34. Most of the time it grades out as a PG 46-34, but every once in a while it grades out to a 52. So it's usually right around a 50, 51 on a continuous grade basis. Okay? So we're not trying to one-up, let's say, the Kraton polymers. What we're trying to say is those are the industry leaders, and say how do these polymers compare to industry leaders? Okay, are we kind of in a reasonable space? So when we go in here, and this is from work from a year and a half or so ago, we can benchmark to the 1101, 1118, and then we can look at the die block versus the tri blocks, and then we can see what we did is we reacted this out at a higher temperature, and that's what produced the better performance grade for us there. Okay, so reaction temperature matters basically. This is what it shows in the RTFO, and so it just says here, this further highlights the fact that with the die block and the tri block, that if we run these out at higher temperatures and blending after RTFO, there was some more chemistry occurring, and that's what we see here. So we have kind of some similar aging going on there. So we can look at the low temperature aspect of things, and we look, pretty good on a continuous grade basis. Okay, maintaining minus 28, and this just gives us continuous grade ranges. Okay. So again, the reaction temperature is pretty important to get something with a broader continuous grade range. Now we start zeroing in, and we want to start focusing in on the molecular weight and the styrene contents. And so this is at the higher level of acrylation. And so we can see at the varying levels that not necessarily higher styrene content produces better results in terms of stiffness. Okay, and so what this shows is that with 3% modification, we can take a 51 continuous grade. Right there it says 52.9, 53.9 was the range. So when every experiment we run blanking samples on the controls. We don't assume that the control is always the same. But this tells us that we're getting at 3% grade, or 3% modification, we're going up quite a bit in temperature range. All right. So there's a pretty famous innovator who said it's really hard to design products by focus groups. A lot of times people don't know what they want until you show it to them. And so that's Steve Jobs. Okay. So I agree with consensus building, but that's probably not the best way of developing innovation. Okay. So now we're going to move out of the lab. So we started off making samples that were, in the lab years ago that were measured in grams. Then we moved to tens of grams. Then we moved to hundreds of grams. Now we're kilograms in the lab, right? Well, every step you go in this, we're now at 50 liter reactors in our labs, and well, when you start getting that volume of solvents in there, our environmental safety people start getting a little bit nauseous with some of these things, right? And you know, in some instances, we're dealing with, you know, younger people, undergrad students who are working in the labs, and they go through training protocols, but you know, when we get to those quantities, it's our professional staff that needs to be involved. So we began on a design build process. So this is just 3D renderings on the design build. So this involved Epic Systems from St. Louis doing the design build for us. So like many of you would pursue in industry, what? You go out, you figure out who are the qualified companies to maybe do this work. You get a pre-designed bids, and then you review them, interview them, then you select 3 to submit more comprehensive bids, and then I work for the government, basically in a university, public university, right? And what do they want to do? Low bid, right? Low bid's not going to yield the best deal here, okay? So I'll explain later how we went into doing some of this work, but we actually were able to pursue the best bid. And so then we hire an external consultant to do a safety review. And then you have to establish what are the standards that you want to have for a pilot plant. Well, you know, university, we're risk adverse, right, when it comes to safety. Chris, what do you think? Yeah, we don't want any fatalities, sorry. Well, okay, well, that doesn't exist. It's really the highest standard in terms of safety review is 1 fatality in 10,000 years. I said, yeah, okay, we'll take that then, okay. Well, then what you get into is if that's the standard we're going to design and build a facility to, we're not going to be dealing with systems that are commonly used in asphalt. We're dealing with pharmaceutical grade equipment, okay? So higher level of safety, higher cost, right? So this is, oh. That's all right. I agree with that message. I can't take the call. So, you know, in my class when I teach, when the phone goes off, I get to answer it. That's what I tell my students. And it happens inevitably every semester. And I get to answer 1 phone call every semester. And it never happens again. So this is at Epic in St. Louis as they're fabricating and building this pilot plant. So they're building it on skids. And so and then we can see different components of the skids going in, some of the reactor vessels and whatnot. So we are taking volunteers to help program the controls for the plant and develop the plant interface. Any volunteers? It's a plug-and-play system. No. So this is where we're taking our plant operators, Austin Homan, Michael Forrester. We're sending them down to St. Louis. They're interfacing with the design build folks and the software engineers building the interface for us. And then the software, what? We want our software to be available on the web, so if we're having some challenges, that Epic can provide that technical support when the plant's operating to interface with us, and we can actually turn control over to the plant to folks in St. Louis, right? Okay. So, beginning in May, we began installing the pilot plant at our BioCentury Research Farm. So this is on Iowa State's property. And this is about 8 miles from campus. And so you can see the installation ongoing here, okay? And then this is the plant before the security fence went up in August of this past year, okay? So this is a $6 million facility. So what we did is Seneca formed a sister company, a couple of sister companies, Argogenesis Chemical and Midwest Acrylated Processes. And so what we reached an agreement on with the university and the companies is that they would design, build it, demonstrate that it works, and then they donate it to the university. Okay? So now this is a university facility, and then Seneca pays us to operate the pilot plant. Okay? So the next question is well, we fast forward more on the research side, and you know, working with some of these folks in chemical engineering, they love to change multiple factors at one time. And I go, we don't know the outcome of what you've done then. And they're kind of more on the science side, and you know, me being an engineer, I'm like, no, can you tell me what had the greatest impact? And then they'll go on, and then I'm like, no, we can't be doing that. So I finally convinced them that we need to have what we call repeated statistical measures design, and we need to develop, you know, basically formulation models, okay? And so that's what we've done. So we created these statistical models using the Flint Hills XX-34. And what it says is that we can come up with, you know, this is based on the higher level of acrylation, so the 2.2 to 2.5 level of acrylation. We can come up with what we would like if we want a certain high critical temperature grade and low grade. We can come up with a formulation. And so, you know, the chemical engineering folks are skeptical of our model, of course. And then they produce I said, well, let's produce, I think it was a 20 kilodalton styrene with 20% styrene. No, maybe it was 10% styrene. At any rate, and I said, well, we should come out with, I think it was, wherever the number was we said we should come out with a 67 grade on high end. They said, there's no way you're going to hit that mark. They produced it, and yep, it was within 0.2 degrees. They said, it's luck. And I said, well, go ahead, make some more polymers for us, and we'll figure it out if it's luck. So, so we've also developed this.
Sometimes you have to adjust the formulation of your product. So how about this new type of polymer? How does it work?
For use in wrap?
No, not wrap. No, different asphalt sources.
Oh, different sources. Yeah. We don't think there's a problem because, I mean, we've looked at the Flint Hills, but then we've looked at AAM and AAD.